sustainability of a rod compressed along the axis, finding the critical force. This is article number 5.1 of book, Mechanical Systems Calculations of the Marine Facilities. We will talk about the possibility of the rod to resist the compression along the axis of the rod. So let's consider the rod. For example, shown on the figure 5.1.1a. So we have the rod supported by the left end at the fixed hinge, and by the right end it supported by the sliding hinge. And the rod experiences the compression by the force F applied to the right end. This rod has a definite deflection, slight deflection. We do not need a big deflection, but anyway, due to the technology of the manufacturing of rod, or the technology of the any misaccuracies of the operation of the rod, or maybe uneven distribution of the temperature in the rod, so it could be the deflections. And the rod, the deflections could be caused by various reasons, physical or technological. The rod is under the compression by the force, longitudinal compression force F. The force F can be applied not to the center of the area of the transverse section of the rod, maybe the force can be not be the very accurate horizontal. The force F can be inclined a little bit. So we no need to the big deflection to explain the phenomenon of the loss of the stability. And the stability is the dependence of the rod bending on the rod compression. If the rod is under the great compression F, so just very slight impact aside to the rod can cause the bending of the rod. So on the scheme, on the figure 5.1.1a, we can see the reference variable x corresponded with the distance from the right one sliding hinge along the rod. Besides, we have the indicated deflection, V deflection, and the length of the rod is L, the force F, etc. The deflection we indicate V, and the bending moment is equal, as it's usual, is equal by the product of the force by the deflection. We are talking about the bending moment in the definite one point of the rod at the distance x from the right end of the rod which is under compression. So we what is the sign of the bending moment? The sign is positive because we have the stretched up fibers of the rod, but actually on the scheme the deflection looks negative. So let's consider the minus sign to the moment. Moment is equal to minus F product by V. V is the deflection dependent on the distance from the right end of the rod, distance x. And on the other hand, we know that the bending moment is a second derivative on the deflection. Deflection as a function of dependence on point location along the rod axis. The reference along the reference axis, we have x reference axis, and the right one end of the rod we consider as a reference point of the size x of this. So as the deflection is equal to the displacement by the bending of definite one point of the rod, we consider this as second derivative as at the moment with exactly the account of the stiffness of the rod. The stiffness is equal to the product of the linear stiffness of the elasticity modulus and by the moment of the inertia of the transverse section. When we consider the loss of the stability, we assume that loss of the stability we denote as the correspondence between the bending moment and the compression force. When we consider the loss of stability, the moment of the inertia of transverse section is minimally available in the transverse section. Perhaps you know that in the transverse sections we have two directions, two perpendicular directions. One direction is of the maximal, the principal directions of the transverse section. One is along the which one direction is around which we have the maximal bending moment, maximal moment of the inertia of the transverse section. Around another one axis on the transverse section of the rod, we have the minimal moment of the inertia of the transverse section. So this is the principal axis of the transverse section. So this is a minimal possible moment, moment of the inertia, the geometric characteristic of the transverse section of the rod, assuming even distributed along the rod. When we substitute the equivalence of the moment in the considered equation, so we will have the differential equation, the equality, the balance of the definite one section point, equality of the moment to the deflection product by the force. We will have, considering the dependence, derivative dependence on the deflection, we can find that we can find the differential equation, second order linear homogeneous differential equation of the deflection independence on the reference coordinate x. So this in this equation we just have to change the symbol. Instead of this one factor f force divided by the characteristics of the elasticity, linear elasticity of the rod, we substitute by k squared. By the k squared is definite one magnitude not dependent on the x, on the reference variable. So the solution of this second order homogeneous equation we have in the form as a product by a by product by sine kx plus b product by cosine kx. This is a well-known decision. I will not talk a lot about that, but I can just explain that for this definite one equation, we can as well have the as the real roots of this equation. So we can have the imaginary root of this equation. So it's not so much important to go in the in deep in the explaining of the what is the roots of this equation. Just only in the within the physical sense, we are interested only in the sine form of decision, sine and cosine trigonometric form of decision of this differential equation. We're not explaining why it is, just due to the physical sense of the result of the definition of the decision function of deflection dependent on x, the decision, the general decision of the linear homogeneous second order equation. Okay. So, and let's do the check when we have the second derivative of this deflection function dependence on the reference coordinate x. We can have the second derivative like indicated here, and when we substitute the second derivative of this deflection into the second derivative and the deflection itself in this equation, we will have the identity to zero. This identity confirms that we do have correct decision of this. Maybe not only this one. Theoretically, we can have another one decision with the exponents. For example, for the other magnitudes of the k magnitudes, the root of the characteristic equation of the this equation have the characteristic, this differential equation have the characteristic equation. So the k is the root of the characteristic equation. So it is out of our interest to go into the depths of the mathematical theory, just only the physical sense have the decision with the sine and cosine, the dependence of the deflection on trigonometric functions of definite k and x variable, reference variable, and a, b constants. So to have the constants, we can set the boundary conditions of the considered issue. So if we will look at the scheme of the compressed rod along the axis, we can find that at the x variable magnitude equal to 0, the deflection is 0, and if the abscissa magnitude is L, the deflection is 0. So, excuse me, let me close the window. There is any work in there. Or any construction outside, I'm sorry. So let's consider the boundary conditions when x is 0, the deflection 0, and when x equal to L, the deflection is 0. So after the substitute, the first one, abscissa x equal to 0, we can find that the b have to be equal to 0 because the cosine of because when we substitute x equal to 0, sine is equal to 0, so we are x equal to 0 due to the boundary conditions, and b have to be equal to 0 due to the cosine of 0 is equal to 1. So b is 0. So of the second one sum, of the first one summed, we have to find a due to the boundary conditions. This will be the conditions of x equal to L, v of v on L equal to 0. This is the boundary condition at the second hinge here. So after the substitute, we can find that if we assume that the decision would be only if a no equal to 0, because the equality this factor to 0, due to we know for sure that the b is equal to 0 to the first boundary conditions, the first one a is not 0, because this decision will not have the physical sense. So we have only the equality to 0 of sine chi x. If a sine chi x equal to L, due to the second boundary conditions, sine chi L equal to 0, is the value next of sine argument is a simple a multiply of p, the multiply of p. So this argument is sine of chi x equal to 0 only if chi x is the multiply of p, that is p product by n with the integer. Then kl, the argument of the sine function equal to pn, due to the equality to 0, the product a by sine having for sure that b equal to 0 due to the first boundary condition. And then we can find that the equality to 0 corresponds to the product k is k squared is f divided by el. ei is the moment of the inertial transverse section of the rod multiplied is k squared by l length of the beam squared, equal to have to be equal to 0, and the x is equal to 0. So pi squared multiplied by n squared have to be equal to 0. And next we can find the Euler's force. Euler's force is force of the Euler of the loss of the stability when the bending moment under the longitudinal compression is more than enough to have the deflection v. This Euler force is p squared by n squared by product by modulus of velocity and product by the moment of the inertia of the transverse section in the direction of the maximal flexibility at minimal stiffness of the transverse section of the beam, divided by L squared. This is considering this formula. Next, we assume that the data when we have only n equal to 1 and I equal to I minimum correspond to the buckling mode of the least stiffness of the compressed rod, wherein the critical force equals, this is a formula of Euler to find the critical force of the loss of the stability of the stretch forwardness property of the compressed rod. The boundary of the condition of the rod can be another one. We can consider the cantilever fastening of a rod, as we can hear the cantilever fastening of the rod. And the same we have decision for the second order homogeneous differential equation related to the deflection. And we have the information about the boundary conditions. We have another boundary conditions. The boundary conditions for the cantilever fixing of the rod is that we have F0, if we correspond the reference point to the right end of the beam, we have F0, zero displacement, zero deflection of the rod at the point of the abscissa equal to 0. And but the left one end of the rod is embedded. In the embedment, we have zero angle of the rotation of the transverse section of the rod. The angle of the rotation is a second derivative, is a fourth derivative of the deflection, or displacement, bending displacement of the rod. And due to the second boundary condition at the point x equal to L, the angle of the rotation of the second dead embedded of the rod equal to 0. So after the substitute into the formula, we can find that as well. We can find as due to the fourth boundary condition equality to 0 of the deflection at the point of the equality of the reference variable to 0, we can find that the b equal to 0, because at x equal to 0, sine of 0 is sine, so all product, the first one summed is 0. So only remains equality to 0 of b cosine is cosine of 0 is 1, b by 1 b, and b have to be equal to 0 due to the first boundary condition. We can next find the first derivative of the general decision of the linear homogeneous second order differential equation of the deflection or displacement of the transverse displacement of the rod under the action of the compressive force on the right hand. And after the substitute in the first derivative, that is in the equation for the angle of the rotation of the transverse sections of the rod independence on the location due to the reference axis x, we can find that 0 is only if the cosine, if the k multiplied by L equal to pi divided by 2 plus multiply pi by n. So multiply pi by n, and the first summand is pi divided by 2. So after the considering, we have the equation of when we substitute the equality of the, instead of the k, we substitute the k squared f divided by ei multiplied by L. Here we have, due to the k squared by L squared have to be equal to this total of the, we can find the minimum zero critical force corresponds to n equal to just a half, the fraction 1 divided by 2, and this is for the moment of the inertial transverse section equal to minimal magnitude in the available for the transverse section of the rod. The critical force at which cantilevered rod loses sustainability equal. So here in the denominator L product by 2, but the first one we had just only L, exactly squared, and here we have squared 2 by L squared. So for this one cantilever embedded beam compressed by longitudinal force, we have 4 times less critical force. And what is about the fastening conditions of compressed rod factor, which impact the rod sustainability in the more general approach for other embeddings and of the ends of the compressed rod. We can draw up the general Euler formula. Formula is about the same 1/4 as the same 1/4 got for this one, the first formula we had for the initial conditions of the rod hinged by the left end for the fixed hinge, and fixed by the sliding hinge, or just only the supporting rod at the other end. And we consider that, and we had the first formula. Like in the numerator, we have pi squared by E modulus of elasticity, and by product by minimal moment of the inertial transverse section of the rod compressed under the axial longitudinal force divided by L squared. The force is the property not of the initial deflection of the rod, is a inherent property of the rod, independence only on the material of the rod, its length and its moment of the inertia of the transverse section, the geometric characteristic of the rod. But in the considering next another possibility of the compression of the embedded rod cantilever, fixed rod, so we can find that the critical force is less. It is like in the denominator in the brackets we have squared 2 by L. First time we had just only L squared. And what is the general formula? Independence on the supports of the compressed rod of the critical force, which is the maximal force for the flexible rod to withstand under the action of the longitudinal force. What is the maximal force the rod can withstand? We can consider the account the conditions of the support of the rod by the factor mu. The factor is a force reduction factor of length, reduction factor of the length of the rod for different fastening conditions has the values indicated in the diagrams in the figure 5.1.2 from A to D. So if we have the hinged support and another one sliding support hinge, the factor is the length reduction factor is equal to 1. We have this, just no reduction factor. Like for the first time, the first option of the boundary conditions, we got this formula is equal to 1. The mu is equal to 1. So if we have the cantilever beam compressed along the axis, we have this factor equal to 2. Mu equal to 2. And if we have the embedded beam, but with a sliding hinge at the other end, this factor will be 0.7. I will not derive this of the initial conditions, but just only offer the ready decisions, the ready decision that equal to 0. So have to be mu for this one kind of the support of the beam. Instead of mu, we have 0.7. And if we have two supports allow the longitudinal compression of the beam, but the one support is embedding, another one not allow the bending of the ends. The factor of the mu equal to 0.5. So this is explaining of the factor of the mu in the more general, the force reduction factor of the length. So how it impacts the embeddings onto the critical force by the Euler formula. And how we can assume that, how we just to image for ourselves. If the beam, the loss of the beam stability, we can consider as half of wave of the sine function, half of wave of sine function, like in two hinges at both ends of the beam compressed here. We can adopt the mu, the length reduction factor equal to 1. If the length of the, to have the length of half wave of sine function, for example, for the cantilever beam embedded by one end and with a free another one end. This is not a half wave of sine function. This is 1/4 part of the wave of sine function, because we assume that here have to be another 1/4 part of the wave, and we need these two beams lengths to have another half of the way of the loss of the stability in the considered option of the embedding of the end, and considering the loss of the stability of the free and compressed cantilever beam. So we have to have two lengths of this beam for the half of sine function of the shape of the loss of the stability. So the mu equal to 2, because we have to have two lengths. For this one now figure of the embedding of one end and the sliding hinge at another end, we for the half wave of sine function, half wave, not for the period of sine function, but half period the wave shape of the sine function, we have here only for the part of our considered compressed beam. So, and here we have 1/4 part of the next one half wave of the sine function. So, as we have to have just only 0.7 part of the length of the compressed beam to locate the half wave of the sine function, like in this definite one considered scheme of the compressed cantilevered beam, and not cantilevered, but embedded by one end and hinged by another one by the sliding hinge. We will have 0.7. That is because within the length of the beam, only 70% about. So to be more exact, 2/3 part of the length of the beam required to locate the half wave of the shape of the loss of the stability. And for this definite one point, we have 0.5, just only half of the length of the considered beam required. We need to locate the half wave of the sine function of the loss of the stability, because the ends not bended, just only the one that embedded, another one slided, but with not bending. The ends of the beam are the 1/4 part to one end and the 1/4 to another one end, contain the parts of the curved axis of the beam, with the rest part of the period of sine function. So in this, the length of this beam, in the considered on the figure 5.1.2 D, the conditions of the connection to the support and to this one, like a, I don't know, the slide, maybe not the kind of the connection allowed the sliding, but not allowed the bending. For this definite type of the connection of the beam compressed by this movable end, we have length enough to locate two half waves of the sine function of the loss of the stability. So if we have two, it means only half wave of this beam to locate half length of the beam, to locate half of the wave of sine function, half wave of sine function of loss of stability. So we will have here mu factor equal to 0.5, half length equal to locate the wave. So this is how the critical force depends on the characteristics of the fastening of the rod. Questions and comments. 5.1.1, the force under which rod, which dimensions and shape of section can be constant along its length, less the mechanical sustainability when compressed along the line passing through the hinges of the supports. This is force is the critical force by the Euler for two ends hinged beam. It is equal to pi squared multiplied by minimal linear stiffness of the rod for the bending divided by L squared, the squared length of the beam. 5.1.2 factors of initial geometric deviations from the straightness of the axis of the elements of mechanical systems and the symmetry of the section shapes. The initial deformation due to uneven heating, initial deformation due to the own weight, technological errors, etc., which are part of the primary causes of loss of mechanical sustainability. They could be the majority of the primary causes of loss of mechanical sustainability. So, but and the accuracy of the manufacturing of the beams in the mechanical systems, the accuracy is important to avoid the loss of the stability on the beams are compressed. But the loss of stability itself is not a characteristic so much of the initial geometric deviations from the straightness of the axis of elements of mechanical systems, but it is in a greater degree the inherent property of the beam length and the linear flexibility. Because in determining the critical force, the force of the loss of stability, the maximal force which a beam can withstand, not losing the stability, the sustainability, which remains compressed, not bulged. This force, this minimal force, is proportional to the elasticity characteristic, or proportional, sorry, to the stiffness characteristic, linear stiffness characteristic of the beam for the bending, and divided by the length squared of this beam. So this is characteristics of the beam itself with not the initial deviations from the straightness. So the critical force is inherent characteristic of the compressed beam, and it fastening to the supports or to the other beams or other elements of mechanical system. 5.1.3, the magnitude of greatest compressive load on element mechanical system, rod, plate, shell, etc., which element is able to withstand without loss of mechanical stability, which is the own characteristic of the rigidity of the system element and the conditions of its connection with the support or with other elements of mechanical system. Yes, the magnitude we can find by the Euler formula for rod finite elements. For other finite elements, like the membranous, no membranes so much, but like two-dimensional elements, etc., we can have another formulas of the stability, another Euler formulas of the stability, which is the considering of the bending under the actual compression of the element of the mechanical system. Dependent on the local or linear stiffness of the element mechanical system, two-dimensional, one-dimensional, and dependent on the support of the mechanical system. On the kind of the support, on the kinds of the fastening of mechanical system. 5.1.4, the correlation of the bending moment arm with the resulting deflection when compressing the element mechanical system on the passing through the hinges of the supports, in particular when compressing a rod along axis, which cause a form of the chord axis equation, including the deflection of the axis, the proportional bending moment arm of the second derivative of the deflection corresponding to the diagram of the bending moment on the scale of the rigidity of the element of the mechanical system. This is just the sequence of the derivation of the second order differential equation, homogeneous to find the critical force, because this is correspondence of two summands of the equation. One summand is the deflection of the and the second and the bending moment or the action of the compressive force on the deflection. So thus we can find, and this derivative equation, because the deflection depends on the as a second integral function on the bending moment. So the bending moment is second derivative, and the arm is second derivative of the deflection is second derivative of the bending moment. That is a concept of the differential equation. 5.1.5, the shape of curved axis of rod subject to axial compression and the solutions of linear homogeneous second order differential equation. The shape of curved axis is the part of the wave of sine function dependent on the kind of the fastening of the ends of the rod element compressed. And if we have at both ends of single span rod finite element, in this case we have the like the shape of the curved axis like a half wave of the sine function hinged by at both ends. For the rod hinged at both ends, the minimum axial force, the Euler force at which the loss of the mechanical stability of the rod on hinged supports at both ends occur. The minimal force corresponds to the fraction. In the numerator we have the constant like the pi squared, etc. And we have as well the characteristics of the linear stiffness, minimal linear stiffness of the compressed rod, minimal linear stiffness for the bending, dependent on the modulus of the elasticity of the material of rod and dependent on the minimal moment of the inertia of the rod transverse section. In the denominator, we have the squared product of the factor of the reduction of the of the length, reduction of the length influence on the critical force. In the we have the product in denominator. This factor of the reduction we multiplied by the length of the compressed finite element, and this total product we consider in denominator. We consider square total product of the mu factor of the reduction of the length by the length. This product in square power to square degree. This denominator and the formula of the Euler force, critical force, which the rod supported by the assigned fastening condition, this rod can withstand. 5.1.7 minimum axial force at which loss of mechanical standability occurs when the rod is cantilevered. The influence of boundary conditions, the conditions of rod and supporting or pinching, or on mechanical sustainability, the magnitude of the critical force. If we consider two compressed rods, one rod we assume is hinged at both ends. The one end is connected to the fixed hinge, another one connected to sliding hinge, and to second end is applied the compression force, compressed the rod, and we will find the critical force which this rod can withstand under the compression, this Euler force, and we'll consider the same rod with the same transverse section and the same material, but the rod cantilevered, embedded by the second end, and by the first end have no the support, so the second end is free, and we will find the force, compressive force, which is maximal available for this definite one cantilevered rod to withstand, maximal possible to withstand. So this critical force will be 4 times less than for the rod hinged by both ends. 4 times less because we have the factor 2, because we have the length of the rod reduction factor 2, and we have this in the denominator in the square degree, so we divided not by 2 but divided by 4 times less critical force available for the cantilevered beam than for hinged beam to withstand if the same section and the same length of the beams and the same material we have. 5.1.8 the coefficient of influence of the rod length on the critical force at which it loses mechanical sustainability depending on the condition of the rod fastening. The factor is could be 1 for the 2 ends hinged rod, could be the factor 2 of the length reduction. The factor is squared. Mu squared factor of the length reduction, independence on the fastening conditions. For the cantilever beam embedded by the second end, the factor is 2 power to square degree, so equal to 4. Finally, the factor can be 0.7 if we have the second end embedded and the first end supported by the hinged sliding hinge. The first end to which we have applied the compressive force, and the factor will be 0.7, the reduction factor of the length influence on the critical force. For this definite one connection, if we compare with the rod hinged by both ends. So for the hinged by the first end on the sliding hinge, and embedded by other hands. At other hand, so we have a factor 0.7 squared to the length. So the force will be 0.7 is about the critical force will be twice greater than for the rod, compressed rod hinged at both ends. And if we don't allow the bending of the ends of the rod compressed, in only we have one end embedded by another end available the longitudinal displacement, like sliding fastening to the support of the end of the rod when we apply to the compressive force. So for this one kind of the fastening, we have the length reduction factor equal to 2. So we have this factor in the square degree. So the beam embedded by one end and at other end having having the support which allows the longitudinal displacement of the end and not allows the bending and transfer displacement. For this definite one kind of the fastening, the critical force will be 4 times greater than for the rod hinged at both ends. 4 times greater because the factor of the reduction in the denominator of reduction of the length influence on the is 0.5 to the squared power. 0.5 denominator to the squared power. This is 4 times excess of the force due to the factor of the fastening condition influence. Thank you.